Hello guys, you're welcome to Dietary Academia. If you've not subscribed to this channel, do well to hit the subscribe button and also share this video. Today we are going to be looking at thermochemistry. All right, so from the word thermochemistry, you should know that we're talking about like two words: thermo, which has to do with temperature, thermal energy, and chemistry, of course, that defines the relationship between properties of matter. All right, so basically thermochemistry is the chemistry of the emission of thermal energy. All right, so when we talk about thermal energy, we should also understand that we are making reference to heat, relationship between heat and energy. Relationship between heat and energy. All right, you know what energy is. Energy is defined as the ability to do work or to supply heat. That's what energy is, the ability to do work or to supply heat. All right, so, and of course there are two major forms of energy. We have the kinetic energy, and we have the potential energy. All right, we have the kinetic energy and we have the potential energy, as you can see. All right, so basically when we say kinetic energy, we have a basic formula for kinetic energy. We represent Ke as half mv squared. M is actually expressed as the mass of the body, then V is the speed or velocity at which the body moves. So the mass is in kilograms, velocity is in meters per second. All right, velocity is in meters per second. So basically the unit for kinetic energy is joules. J is joules. All right, J is joules. Okay, so if we have 1000 joules, that is 1 kilojoules. This is 1 kilojoules. All right, so bear that in mind. Okay, so moving forward, one thing I need you to also understand is that when it comes to kinetic energy basically has to do with the energy of a body when the body is in motion. So motion talks about movement. So when the body is in motion and you're trying to calculate the energy of that body, then that is the kinetic energy you're trying to estimate. All right, so another thing that we'll look at is this guy here, which is called potential energy, denoted as PE. All right, so potential energy is the energy stored. Okay, is the energy that is stored in a stationary object, okay, due to its position or condition. Remember, I told you kinetic energy has to do with when an object is in motion. All right, but potential energy is called stored energy. All right, so when we say stationary object, a stationary object means that the object is fixed at a point. All right, it's not moving. It is stationary at a point. Okay, so when it is moving from, let's say, point A to point B, that is the time that we have to calculate the kinetic energy. But when it is stationary, when it is fixed at a point, then it is what? Potential energy. All right, so the energy of a body when it is fixed at a point, the energy of a body when the energy is stored in a stationary object, all right, due to whether it's position, due to where it is, or the condition that surrounds it. Okay, that's what we call the potential energy, the stored energy. All right, so examples of potential energy we can actually relate to this is, you can say a boulder at the top of a mountain. All right, you know it will be fixed at that point. At the top of a mountain, it will be, let's say we have a mountain, then we have a boulder at a point on the top of the mountain here. All right, so it will be fixed at this point. So when it is fixed at this point, it's not moving. So the energy that is stored in the object that is fixed at this point, that's what we call the potential energy. All right, that's what we call potential energy. So that's a typical example. So but when it begins to roll down, when it begins to roll down, it no longer becomes potential energy. If it begins to roll down the mountain, all right, so at that point what we'll calculate to be kinetic energy, because it's no longer stationary, it is now in motion. It's no longer stationary, it's now in motion, that is now exhibiting movement. All right, it's now exhibiting movement. So basically we'll be looking at how to calculate heat content. Okay, we'll calculate how heat content. Okay, so one thing I need you to understand is that basically kinetic energy of a system, all right, kinetic energy of a system usually emit heat. Okay, it's very important to know that. So when we want to express the kinetic energy, okay, realized by motion and collision, we refer to it as heat. Okay, so we refer to it as heat. So anytime we want to actually measure or express the kinetic energy that has been realized when a body is in motion, okay, or where there is a collision between two objects, where there is a binding between two objects such that they collide together. So whenever we want to calculate motion or collision with respect to kinetic energy, at that point in time, what we are trying to calculate is the heat content. All right, is the heat content, because it's heat that will be produced in the process. All right, so one thing you need to understand, that the unit for heat, okay, is joules. Okay, but a more common unit that we are familiar with is called calorie, in brackets cal. Okay, so cal is usually used as well, but it can also be expressed as what? Joules. All right, so it can also be expressed as joules. All right, so basically we can define calorie as the amount of energy that is required to raise 1 gram of water. Okay, the amount of energy that is required to raise 1 gram of water. Okay, so basically 1 gram of water has a temperature of 1 degree Celsius. All right, the temperature of 1 degree Celsius, which is also 273 Kelvin. All right, 273 Kelvin. So usually when we want to define calorie, okay, we use this is the best definition. So the amount of energy that is used to raise 1 gram of water is known as a calorie. So there's what we call dietary calorie. Dietary calorie is the calorie or that is present in the diet. Okay, so dietary calorie is equals to 1000 cal. All right, 1000 cal. And like I told you, calorie is expressed in cal as the unit, cal. Okay, another thing you need to understand is that when you want to convert from, let's say you want to convert from calorie to joules, okay, you need to note that 1 cal is equals to 4184 joules. All right, 1 cal is equals to 4184 joules. So this is actually the relationship between calories and joules. All right, so we'll be looking at an exercise straight away. I'm going to be reading it out for you now. A 30 grams portion of fat contains 11,000, or let's say 1,100. Let's just use 1,100 kilojoules of energy. I will take it again. A 30 grams portion of fat contains 1,100 kilojoules of energy. How many dietary calories would that be? All right, so we are being told that dietary calorie is actually the amount of calories, all right, that are in a particular diet. And I told you that standard dietary calorie is 1,000 cal. So you want to actually know how many dietary calories would be in 30 grams of fat that contains 1,100 kilojoules of energy. All right, so how do we solve that? All right, so the amount of, okay, let's say solution to this question. So the amount of energy, okay, E that you have here is 1,100 kilojoules. Now I told you initially that if we have 1,000 joules, it is equals to 1 kilojoules. But basically, the unit for energy is meant to be expressed in terms of joules. So what do? We have to convert these kilojoules to joules, and we do that by multiplying by 1000. So if we are to multiply by 1000, this will give us 1 million. Okay, 1 million. So we have 1,100,000. All right. Okay, so okay, 1,100,000, and we have 1.1 million. Let's confirm it. Let's be sure. So we have 3 here. We have 2 here. Okay. So we have, yes, 1.1 million. That is 1,100,000. All right. So basically, if we are to use this, okay, that is in joules. If we are to use this that is in joules, okay, we have to express this particular energy in terms of calories. That's what we are being asked to do. We are being asked to actually determine the number of calories. Okay, so having converted this to joules, the next thing to do is to convert it to calories. So recall, initially I gave you, so recall that 1 calorie is equals to 4,184 joules. So if 1 calorie is equals to 4,184 joules, so we can say X calorie is equals to 1,100,000 joules. Okay. So if we cross multiply, it means that our X calorie will be 1 cal times 1,100,000 joules divided by 4,184 joules. If joules should cancel joules, okay, joules should cancel joules. So this is what we have. So we'll say 1 times this. 1 times this is still this. So we have 1,100,000 divided by 4,184. Okay, so this will give us 262.9, which is approximately, okay, 262.9, which is approximately 263 calories. So it means that in the 30 grams of fat, we have 263 calories. So we are not expected to use these 30 grams because the 30 grams of fat has already been estimated to be given this. So we are not expected to use this. All right, just in case you thought that we'll use this value, no. This is what we are trying to relate. We are trying to relate the energy with the calories, and that's what we simply did, and we're able to convert, and we got 263 calories. All right. Okay, so I would like you to try this question. So you can write your answers, you can type your answer in the comment box below. So like I said, just convert your kilojoules to joules by multiplying by 1000. After that, convert from calories to joules. I told you that 1 cal. So just relate this first. You say 1 cal is equals to this. So it means that X cal will be equals to what you actually got. Now, if your energy is already in joules, there is no need converting. All right. So X cal, now we just cross multiply. You say this times this divided by this. That's cross multiplication. Multiply this by this, then divide by this. So we have 263 calories. So please try this question. Now it's 25 gram sample of soda pop contains 2,500 kilojoules. Okay, 2,500 kilojoules. So how many calories does the soda pop contain? Okay, how many calories? So it's the same method. So please use this quickly and solve for the amount of calories that are present in this amount of energy. All right, so like I said, type your answer in the comment box below. All right, so we have another question in front of us. Say, how many kilojoules are in a candy bar containing 750 calories? All right, so if you look at this question, you realize that we have the calories and we are told to look for the energy, all right, which is, of course, the kilojoules of the energy in the candy bar. All right, so if you look at it very well, you realize that it's now like direct opposite. Okay, before we were looking for calories, we had kilojoules. Now we are being told to look for kilojoules from calories. So how do we do that? It's very simple. All right, so the solution to this is very, very easy. Okay, now we have to first of all show the relationship. Always show the relationship between kilojoules or joules and calories, like we stated initially, that we have 1 calories to be equal to 4,184 joules. 4,184 joules. So now we say if 1 calorie is equals to this, since we are looking for the joules, we cannot actually get kilojoules now. We have to get joules first, so we'll later convert to kilojoules, because the relationship here is between calories and joules, not calories and kilojoules. All right, so if 1 calorie is equals to these joules, then we say 750 calories will be equals to x joules. Are you seeing it? 750x, because this is what we are looking for. This is the unknown. So what do we do now? We cross multiply. So we say 1 calorie times x joules is equals to 4,184 joules times 750 calories. Okay, 750 calories. So now we want to make x joules solid to a formula, since that's what we are looking for. So it means that our x joules, we divide both sides by 1 calorie. So divide both sides by 1 calorie. Calorie will cancel calorie here. 1 calorie will cancel 1 calorie. So x joules will be equals to 4,184 times 750. And this will give us, let's do it. Let's calculate it. Let's calculate it quickly. So we have 4184 times 750. So this will give us 3,138,000. All right, 3,138,000. So by the time by the time we actually have this now, if you look at it now, x now is in joules. So this is in joules, but this is not our final answer. All right, this is not our final answer. We have to divide it by 1,000, so we can convert it to kilojoules. Remember, when you're converting from kilojoules to joules, you multiply by 1,000. But when you're converting from joules to kilojoules, you divide by 1,000. All right, so if these 3 zeros cancel these 3 zeros, so our final answer will be 3,138 kilojoules. All right, so that's our final answer. So it's very easy. All right, so I want you to try this out. So try out this exercise and drop your answers in the comment box as well. So calculate the number of kilojoules in a potato containing 105 kilocalories. 105 kilocalories. All right, so the tip to that is that with that 105 kcal, you have to convert it to calories, you have to multiply 105 by 1,000. All right, multiply 105 by 1,000, then solve. It's quite easy. So convert this, okay, convert this to calories, then you show the relationship between calories and joules. All right, so when you've converted it to calories, you say if 1 calorie is equals to 4,184 joules, then that value, of course, 105 times 1,000, it will be 105,000 calories will be equals to x. All right, so make x solid to a formula, make x solid to a formula, and solve it exactly the way I've solved it here. All right, so quickly we'll be looking at exothermic and endothermic reactions. We're still in the series of thermochemistry. All right, so basically I'll be defining what exothermic and endothermic reactions are. All right, so exothermic reactions are chemical reactions that release heat to the surroundings. All right, so whenever a chemical reaction has the ability of releasing heat to the surrounding, is called exo. Exo means outside. All right, so that's exo. All right, so basically an example is what we call, an example of such reaction is what we call combustion reaction. Combustion reaction. And a combustion reaction is a reaction where an organic compound burns completely in the presence of oxygen gas to liberate carbon dioxide and water only. Okay, so a typical example of a combustion reaction is the reaction between let's say propane is C3H8 and 5 molecules of water. So what will be liberated will be 3 CO2 plus 4 H2O. All right, so these will be the products. Like I told you, only carbon dioxide and water will be formed. If you look at it, it's a balanced reaction. This is propane. Propane is a typical hydrocarbon. All right, so this, of course, oxygen gas, then CO2 is carbon dioxide, then we have water. So basically one thing you need to understand is that there is also another product that is formed, but it's not actually a compound. All right, in a combustion reaction, when carbon dioxide and water are formed, all right, heat is also released. Heat is also released. So heat is, we also consider heat as a product, because I told you that in an exothermic reaction there is a release of heat. So when you say there is a release, it means that that particular heat becomes a product here. All right, so please, I want you to take note of that. All right, so so that's a basic point that you have to take note of. So any other reaction, any other combustion reaction as well can play the same role. It doesn't have to be only propane. All right, so other combustion reactions, they release carbon dioxide, water, and of course heat in the process. They are all exothermic reactions. All right, so it's important to take note of that. So when this 1 mole of propane is actually burnt in the presence of oxygen gas, okay, the amount of heat that is released is a standard value. Okay, so it is 2028.8 kilojoules. So this is the amount of heat that is usually released in the process. But one thing we need to understand is that due to the pattern at which the heat is actually released, it's not usually released in a forward direction, usually released in a reverse direction. So when this heat is actually released, the value sometimes will tend to express it as minus 2028.8 kilojoules. Okay, so this is the amount of heat based on the convention of the heat of the reaction for the combustion of this propane. We tend to have this as a standard value, so please don't forget this value. This 2028.8 kilojoules. Remember, you can also convert this to joules by, of course, multiplying it by 1000. All right, so it's important to take note of that. Okay, so another point that I have to make about this is that in the process of that reverse direction, there is usually a loss of heat. All right, so there's usually a loss of heat. That's why we have negative here. So there's usually a loss of heat. So when heat is lost, most times the energy that is being expressed is usually expressed in terms of negative. Now we'll be looking at endothermic reactions. All right, so we're looking at endothermic reactions. So what are endothermic reactions? So the endothermic reactions are chemical reactions that needs to absorb heat from the surrounding. Remember, exothermic releases, but this one absorbs heat. Okay, so they do that in order to actually proceed. Okay, they do that to proceed in the reaction. If they don't absorb heat, they cannot be able to proceed to form products. All right, so a typical example is the formation of nitrogen monoxide. We know nitrogen monoxide as NO. Okay, so when nitrogen monoxide is formed from nitrogen gas, okay, and oxygen gas as well, which is expressed as O2. Okay, this is a typical example. So the reaction is usually, we can 2NO here. Now we now have N2 plus O2. All right, so this is the balanced reaction. So this is an example of an endothermic reaction. Okay, basically this chemical reaction does not explain thoroughly about endothermic reaction, but one thing you need to know is that the reaction will not proceed. Okay, the reaction will not proceed to N2 and O2. Okay, if peradventure there is no absorption of heat. So like I told you, for an endothermic reaction to actually be made possible, heat must be absorbed from the surroundings. All right, it must be absorbed from the surroundings. All right, so that's a very vital information you need to actually take note of. So for NO now to be formed, okay, for NO now to be formed, there need to be a reversible reaction. All right, reversible reaction. N2, nitrogen gas, now will react with O2. Then we'll use our half arrows to show reversibility. All right, to form our 2NO. This is a gas. They are all gases actually. This is a gas, this is a gas as well. So this is actually the balanced reaction, the major reaction for an endothermic reaction where 2NO is formed. All right, this is dissociation of NO to form nitrogen gas and oxygen gas. This is the reversible reaction. Usually we tend to use a reversible reaction sign here as well to show that this particular product, set of products, can also come back to form the reactant. All right. All right, so quickly we'll be looking at the relationship between thermochemistry and states of matter. Okay, we know that the different states of matter, we have solids, we have liquids, and we have gases. All right, so we know that solid materials are the materials that have a definite shape, they have a fixed shape and volume. All right, so and the arrangement of atoms or molecules in a solid, everything they are fixed. Okay, so because the arrangement of molecules in a solid is fixed, then because of that, the atoms or molecules in a solid tends to actually move very slowly. Usually slow movement, all right, which is still talking about kinetic energy and all of that. So the movement is usually slow. All right, so for liquids are actually materials that have definite volume, okay, but unlike the solids, they do not have a definite shape. They have an indefinite shape. So the arrangement of liquid atoms is random. Okay, when it comes to atoms and molecules, the arrangement, the movement is random, unlike solids that are fixed. Okay, so the shape of a liquid is usually dependent on the container. Okay, the container where you actually place that liquid. If you place the liquid in, let's say, a cup, you place the water in a cup, what happens is that the water tends to take the shape of the cup where the water is in. All right, so it takes the shape of the container. All right, so that's something that's very, very important for you to take note of. All right, then their movement, just like I talked about solids. I said solids tends to actually have very slow movement of atoms and molecules, but for liquids, their movement is usually faster. Okay, it's usually faster because like I said, atoms and molecules tends to be arranged in a randomized manner. All right, then for gases are materials that have an indefinite shape and volume. Okay, this one have indefinite shape, but they have definite volume. All right, this one both definite volume and definite shape. Gases, both of them are, both shape and volume are indefinite. All right, but one thing about the shape and volume of gases you need to understand is that it's actually determined by the shape and the volume, okay, of the container that is holding the gas. So whichever container is holding the gas, it tends to actually determine the shape and the volume of the gas. So the movement of atoms are very, very rapid. So from slow to fast to rapid. All right, I want you to understand the difference. So quickly, we'll be looking at the changes in the states of matter. So basically, when we look at changes in state of matter, there are 6 changes. We have the melting, we have freezing, okay, we have evaporation, evaporation is also called vaporization. All right, we also have what we call condensation, then we have sublimation, and lastly deposition. All right, deposition is also called desublimation. Let me just explain them quickly. Melting is actually the change of state from solid to liquid. When it's solid, like ice, when ice is actually melted to water, ice is still water but in solid state, while the water that we know is water in liquid state. So when ice is actually melted to water, we call it melting. That's the change of state from solid to liquid. Then now freezing is actually the change of state from liquid to solid. All right, evaporation is the change of state from liquid to gas. Liquid is like this water now being transformed to steam. That is H2O in gas. It's called steam or water vapor. All right, then that's evaporation. Then condensation now is when you now convert this steam, okay, this steam that you converted from liquid to gas, when you convert it back to liquid. Okay, when you convert this steam back to liquid, back to the water, just like when you're boiling water, now you would see some water molecules at the top of the cover of the water. So it is because of the steam that evaporated that was converted back to the liquid. So that is called condensation. Then sublimation is the process by which a solid substance, okay, like charcoal, is being converted to gas. okay, gas like smoke, okay. So convert it like charcoal, you're burning charcoal, then smoke starts going up. So that's an example of sublimation reaction. Then deposition reaction now, it's when this smoke, like for instance smoke from exhaust pipes of generators, when they are converted now to charcoal, you put your hand in the exhaust when it is off and you're touching charcoal, that is called carbon monoxide, which is CO. So that process is called deposition. All right, so I want you to understand that all of these play a role in the formation of heat. All right, it plays a role in the formation of thermal energy one way or the other, especially through motion. You know, these molecules and particles, they're actually moving. All right, so when there's kinetic energy, the amount of energy that at that point tends to actually lead to the generation of heat. All right, so it's very important. Then I want to quickly define what is called phase diagram. Phase diagram, all right, it's another important concept that you need to know. Okay, so when you say phase diagram, what do you mean? So phase diagram, the phase diagram of a substance shows graphically, okay, as a function of the relationship between temperature and pressure. Okay, all right, so it shows a graphical representation of temperature and pressure, okay, of a particular substance. So for instance, now if we want to draw, I will just quickly draw the phase diagram of water. All right, so this is the phase diagram for water. Okay, so one thing you need to understand is that in this phase diagram there are three areas that shows the three states of matter. We have the solid, we have the gas, we have the liquid. These three areas. Now the solid, if you look at it, the solid is above the curved line. There is this above this curved line. Okay, just below the melting point line. All right, then if you look at the liquid is above the curved line. There is this line here. There is this particular one is above this other curved line. You see I separated them. All right, so the liquid is above the curved line, but to the right of the melting point. Okay, to the right of the melting point. So this one is to the left of the melting point line. This is the melting point line. Okay, so if you look at it, the liquid is to the right. I'm trying to explain the phase diagram. Okay, then look at the gas. The gas is now below the curved line. Look at the curved line here. This is the melting point line. All right, then another thing, the triple point is the point where all these three phases, okay, are actually at equilibrium. Okay, where the three phases are at equilibrium. What is equilibrium? Equilibrium talks about balance. All right, so where they are at equilibrium, so basically the point is actually at this point here, and it is usually 0.006 atm. That is atmospheric pressure. All right, so atm here. Then in terms of temperature, we usually express it as this particular point here. Okay, so this is pressure against temperature, but the most important thing is actually to know the value of the triple point, which is 0.006 atm. All right, so that's for the triple point. Now another one is the critical point. Okay, this is the critical point here. So if you look at it, it is the point at which a gas and a liquid are indistinguishable, when you cannot distinguish between a gas and a liquid. So that's this point is called the critical point. Another thing you need to know about the critical point is that the critical point is actually due to a very high temperature. Okay, so it happens due to a high temperature. For you not to be able to differentiate between a liquid and a gas is because of an increase in temperature. All right, and also an increase in pressure. Not just an increase. If you look at it, look at the point is at the peak. Okay, if you look at, see, this is the temperature axis. This is temperature axis. If you look at the critical point now, it's towards the end of temperature. Then for pressure, it's towards the end, towards the highest point, the apex point of the pressure. So it's usually at this point that it will be difficult for you to actually distinguish between the liquid and the gas. All right, so basically there are values for it. So the critical point has a standard value of 374 0.4 degrees Celsius. And you look at how large this temperature value is. It's even higher than the standard value in Kelvin. And of course 217, that is at this point now we have 217.7 atm. That is at this point we have 217.7 atm, while at this point down here we are saying that we have, that is, if you trace it down, if you trace this down, this will be 374.4 degrees Celsius. All right, so that's important. That is something important for you to know. Then look at this other one. It says supercritical fluid. So when the substance is above the critical point, both for critical temperature and critical pressure, then that substance is considered a supercritical fluid. Don't forget that. So when it's above the critical point for the temperature and critical point for the pressure, it is called a supercritical fluid. So that's one thing you should take note of. All right, so that is that for thermochemistry, introduction to thermochemistry. So in our next video we'll be looking at advanced thermochemistry, where we'll be looking at the different laws of thermodynamics, and of course we'll also be treating Hess law. So if you've not subscribed to the channel, do well to hit the subscribe button so you get notification on when we post our subsequent videos. All right, thank you, and see you in the next class.